today we will be talking about molecular transport phenomena. This is our first foray really into fluid mechanics, and here the central notion is that random particle motion can give rise to macroscopic phenomena. And this really is captured by this concept that you've all heard of diffusion. And I'll illustrate this with a thought experiment here. So imagine you have a space, and I'm just going to draw it in 2D, that is filled with a mixture of, say, nitrogen and oxygen. So these red dots represent my oxygen particles, and green dots represent nitrogen. So we have a non-uniform mixture. So we have a non-uniform mixture of oxygen and nitrogen. The way I've tried to draw this here is that the mass fraction of my, say, nitrogen decreases on a line that is perpendicular to this line AB. So overall, in this space, we have a density rho. The units of rho are kilograms per meter cubed. And if we look at a certain element in here, then the concentration of nitrogen is C, which is the density rho times the mass fraction Y. So capital Y is mass fraction of nitrogen. And I've postulated that this varies along a line that is perpendicular to the line AB. Now, the differences in concentration with high nitrogen concentration down here and then less as you go up to the top right, that is what drives ultimately the diffusive mass flux in the direction perpendicular to the line AB. And this mass flux is typically written as J, and it is a vector since it has a direction. And since this is a mass flux, it has the subscript m. And now we have all the ingredients really we need to describe how fast this flux is. Namely, Jm is proportional to minus the gradient of the concentration, which is minus rho times the gradient of y. And that's because we've assumed that the density in this space, i.e. the number of particles in the space, doesn't change. So we assume rho to be constant. And whenever we have a proportionality, then we need a constant of proportionality. And in this case, this is the mass diffusivity. So Jm is equal to minus the diffusivity d times rho times the gradient of y. And this relationship is known as Fick's law of diffusion. And it is named after a German-born physician and physiologist, Adolf Fick, who came up with this law in 1855. And this in Germany at the time was a period of strong beards with a little bit of styling of the mustache. Now, just to briefly review, why is there a minus sign here? Well, it's because our flux will go from high concentration, from high Y mass fraction to low. And you can readily see why that implies that there needs to be a minus sign if you want to have this to be the direction of the flux. Namely, if we look back at our direction of diffusion here, and we go from, say, one point x1 to another point x2, from high to low, x1 to x2, then our mass fraction, if that's a function of x on the vertical axis, and then we go from a high value to a low value, and in this case the gradient of y is just dy by dx, and this is negative since we're going downhill, but we want our flux to be positive in this direction. Jm needs to be a positive number as we increase x, so to balance out the negative sign from the gradient you need another negative sign in your diffusion law. And so what does J of m do over time to our mixture? It homogenizes or smoothens out the distribution. So if at some time t1 you start with a mass fraction that varies greatly between x1 and higher values of x, then at a time t2 later on the mass flux from low to high values of x, j, will lead to a less steep gradient, and at an infinite time t infinity this will actually be uniform across the whole space. So at T infinity, our mixture between nitrogen and oxygen will be perfectly mixed. And so even though individual particles move randomly, if we look at a large number of particles, you see that there's a predominant flux from high concentrations to low concentrations. And this is what we call Fick's law of diffusion, and this is a diffusion of mass.